So I'll just take a moment to introduce Dr. Ashraf Al-Far. Dr. Ashraf is the Secretary General of the Arab Federation for Dates. So he's a kind and dear friend. We know each other from like previous collaboration in other conferences. So Anthony, are you ready?
Yes.
Okay.
Okay, I'm ready.
Okay, so can you respond to Dr. Ashraf's question?
Yes, it's part of our projection as an institution is to develop a model and whereby we are going to show to the whole world the demo. The demo we showcase the quality of the product we are producing, and whereby we want to develop a mini structure that will last for like a period of 2 years again, whereby we're going to put, we're going to use it to house animal and see and take a daily measurement of the temperature, the relative humidity to see how efficient the material will be if it is used properly in construction. Because part of the objective of the research is to sell to the whole world that we can use an alternative material from agricultural waste and our coconut fiber by reinforcing. Because of another thing from this research that when we carry out the what is it called, the thermal property, the thermal property of those materials, we discovered that the ambient temperature when you are inside the roof trusses is cooler than when you use the normal conventional sheet material. So our projection as an institution is to develop a model whereby we are going to have a demo for the whole world to see that after a period of so years, these are the achievements, and we can recommend it globally that if you produce fiber-reinforced cement composite using that method, it can be as a substitute for using other conventional, and which is very readily cheaper than using conventional.
Thank you.
Thank you, sir.
Thank you, Dr. Anthony. So I think our final presentation for the day and for the entire conference will continue with Dr. Anthony. He has a second presentation, which is titled The Effects of Selected Cement Admixtures and Accelerated the Curing on Physico-Chemical Mechanical Properties of Coconut Husk Fibers, Reinforced Composite Roofing Tiles. So I think this is a continuation of the work he just presented. Dr. Anthony, please start your presentation.
Thank you. Good day once again. This is continuation of the previous presentation I made, and we are going to have a clear understanding of what I've been speaking about earlier on. This afternoon, okay, I think it's evening Malaysia, I'll be presenting on the effects of selected cement admixture and accelerated curing of physico-mechanical properties of non fiber-reinforced composite. Now, as we all know, cement composite are made from a combination of wood fibers, strands, and other liquid material in cement production. Now, for us to produce a good cement bonded composite reinforced with the fiber, and some of the fiber used in this experiment is coconut fiber. Then, another thing why we have to develop an alternative way to solve the problem of roofing material is cost and availability of conventional roofing material. And this led to search for an alternative roofing material from both agricultural and industrial ways. Because roofing material are not generally available, and most times if they are available, they are highly expensive, and which affects most of the construction work in developing world. So now, the effect of carbonation I explained in my previous. There are two methods of carbonation that we use in our own research institute. There's one we call wet carbonation. There's one we call dry carbonation. For this paper now, for this particular I'm presenting now, I'm using dry carbonation for this one. The one I explained before is wet carbonation. And in this one, we are going to see the difference between the two. Why do we need to use wet? Why do we need to use dry carbonation? Now, from what I explained earlier, carbonation lowers the pH of cellulose fibers, decreases the alkalinity and enhances chemical hydration of fibre-cement composite. Based on the question Prof asked the other time, this answered the question that the carbonation it decreases the has the chemical hydration between the composite material, the matrix material. Also, carbonation helps in densification of the cementous matrix and reduce the permeability and porosity, which constitutes a positive sealing properties of the cement. That's in line with what I explained earlier. Now, the objective of this particular study is to study the performance of admixtures, rhizose ash, calcium carbide with, and chicken eggshell, and partial replacement of cement for the production of fiber. Now, the difference between these and what I presented earlier is this. In this particular paper now, we are adding two materials together. We're adding rhizose ash plus chicken eggshell ash. Then we're adding chicken eggshell ash plus calcium carbide. So we're improving on the admixtures to see if there will be a better performance when we bring in more material than when we are using single material. And then also to determine the effect of accelerator on the physical and mechanical properties of the fibre-reinforced composite. Now I want to find out of what value, of what advantage is dry accelerated carbonation on over the wet carbonation earlier. Now, these are the material used for this experiment, similar to those one used. But there's something significant about this particular, which I would like to explain briefly. Now, for this one, the coconut length was chopped to about 15 mm. Why this? Because in our preliminary study, we have to reduce the dimension of the length of our coconut fiber because we are bringing too many materials together to replace the cement. Then our eggshell, the same way, was at 800 degrees Celsius. But in this case, for the eggshell, our eggshell was born at two different temperatures. One at 500 degrees Celsius and another one at 900 degrees Celsius. Why the difference? Now, for the one born at 500 degrees Celsius, I explained earlier that this one is to remove the organic matter in the eggshell. But when you burn your eggshell at 900 degrees Celsius, you know our eggshell consists of calcium carbonate. But when you increase the temperature, you are going to remove the CO2 from the calcium carbonate. When you remove the CO2 from the calcium carbonate, you are going to have calcium oxide. And calcium oxide is a reactive material with cement. And we are going to see this in the course of this presentation. Why the value of our composite has to increase? Because we have converted most of the calcium carbonate from calcium carbonate converted to calcium oxide. And likewise, the eggshell ash was sealed with 75 micron, and the same thing with our calcium carbide. Now, these are the formulation used for this one. The same thing we use our fiber for 4% and 6% by volume of cement, then cement water ratio 0.4, our cement sand ratio. Then we introduce something again in the course of this particular experiment. We introduce methyls. What's the function of a methyls? Because at this stage, we're already adding two more material. And we don't want to change the composition of our water cement ratio from 0.4. What methyls does is to create a good surface area of bonding for our raw materials. Whereby in plain time, it's like it reduces the quantity of water you need for the mixture. So I use our methyls as 0.3% volume of the cement, the total volume of the cement used for the experiment. That's why we have to introduce the 0.3% of methyls so that we will not change our water cement ratio from the initial one used for the wet carbonation. Then hydrolysis of chicken eggshell ash. Now, I need to make us to understand something again. I told us that the eggshell consists only of calcium carbonate. When you burn it at 900 degrees Celsius, it's going to come to calcium carbonate. But because the eggshell ash is an expensive raw material, and if you use it in a mixture, it's going to affect the composition of your composite. Therefore, we need to first of all hydrolyze the calcium oxide. And when you hydrolyze the calcium oxide, you are going to get calcium hydroxide. And calcium hydroxide is a good product in chemical reaction with a cement. And therefore, that's what led to some of the improvement we are going to see in the result very soon. Because when you react water with calcium oxide, you're going to get the calcium hydroxide. Now, why do I have to do it in 1 part by 3 parts? These were based on preliminary trials of experiment because there's no one has ever worked on this formulation from all the researchers I've tried on how to hydrolyze the eggshells to be used in composite production. And these are the formulations: 70% limestone Portland and 50% eggshell, 70% 50% calcium carbonate, 15% eggshell ash. So let me just take it. Now, these are the production methods, not that different from the one I previously explained, and they follow the same trend. But now, the acceleration of carbonation using dry carbonation, this one was subjected to 9 hours CO2 carbonation. Why? Because this one is dry. And you remember in the previous one, I explained that after carbonation for 4 minutes, you leave your sample for a period of 24 hours soaking, whereby you've already injected your water with CO2. Now, the chamber is 60 degrees Celsius, the relative humidity of the chamber is 60. Then something was introduced to determine the level of penetration of our calcium CO2, to see how deep the CO2 is injected into the sample, how deep is it in the composite material. Now, this is our carbonation chamber. All the samples were loaded, you close the chamber, and it's automated. So we regulate it, and then after the 9 hours, you bring out your sample. But in between, and every 3 hours, you cut a fraction of your sample, and you spray it with a phenolphthalein. When you spray with a phenolphthalein, now the colorless part shows the area that has been injected very well with CO2. But the purple area shows that this particular section has not well been injected with CO2 properly. So this was done at the first 3 hours of the experiment. Now, these are the property tests carried out on this particular experiment: the bulk density, the density, thermal degradation temperature, the mechanical properties, the MOR absorption properties. Now, this is the bulk density of the composite material. Now, if you look at the thermal, the accelerated, and the accelerated. If you look at the flow of this table, you see thermally cured sample, accelerated carbonation, accelerated carbonation. One was done for sample incinerated at 500 degrees Celsius. One other one was done for sample for eggshell incinerated at 900 degrees Celsius. Now, thermal curing, what's this thermal curing all about? We are all familiar with conventional curing method, but this thermal curing is an upgraded method of curing sample, whereby you load your sample in a thermal chamber that has of about 60 degrees Celsius temperature. The steam from the chamber is going to cure your sample. So we introduced that to upgrade the efficiency of our raw material, because over time it has proven to be better than using the conventional curing method. And these are the values we got for them. And from the experiment of the sample, we find out that for the eggshell incinerated at 900 degrees Celsius, it has a better performance. Although the bulk density increases, but at 500, the bulk density was lower. But from all the formulations, composite containing rice husk ash and eggshell ash has the lowest bulk density. It shows that the introduction of our admixtures, different raw material, still give us a composite that has lower density than the control, which shows that in our production of roofing tiles, we can use this admixture because it still gives us a better performance than the control. Now, this is the modulus of rupture, the rupture of the material. If you check from the previous slide, the rupture of the material was very low, but because of the introduction of 2 admixtures and changing the incineration temperature for the raw materials, because for all the formulation, eggshell was added, because of the introduction of the hydrolysis that we carried out for the eggshell. So we find out that, and for eggshell incinerated at 900 degrees Celsius, calcium carbide waste perform best. We have about 12.9. That's 12.9 megapascal, which shows a good performance because of the hydrolysis. If you check the one that we did not hydrolyze, we have 9.4. So it shows that the hydrolysis of our eggshell to calcium hydroxide gives us a good affinity for chemical reaction, which gives us a good performance for the composite. Then again, the modulus of elasticity of the material, it's triple. It jumps off from the previous presentation I had. Let's look, for example, for the one that was thermally cured, they are very low. But for the one incinerated at 500 degrees Celsius and the one incinerated at 900 degrees Celsius, you see the difference. And from this experiment, in terms of modulus of rupture, it was the one that contained rices that performed. But in this case, it was the combination of the one that has rice. No, it was the control that performed. No, it was the combination of the one that has calcium carbide waste that performed better out of the 3 admixtures, which shows that the hydrolysis carried out on that particular on our eggshell ash has given us to double the result of performance of our composite type. Now, the flexural, the toughness of the material, how tough is the material? Because this has to be considered when you are using material in an open system, because anybody can easily throw an object on your material. Now, from the detail of the result, it shows that as we improve on the method of production, the toughness of the material equally increase. So therefore, it's recommended that for anything we want to use our eggshell, it's better we improve or we hydrolyze our eggshell high. Now, the water absorption level. This shows the water absorption level for all the three categories of population that we use. And from the experiment, it shows that at the one incinerator at 500 degrees Celsius, we see our calcium carbonate, which has the lowest. And the same thing happens at 900 degrees Celsius. Why? Because of this. Because calcium carbide waste is a finest particle, which allows good bonding better than other raw material. It's so finer. So it helps in a good chemical reaction. And as when you change the chemical reaction of calcium carbonate, it has a close chemical reaction close to the cement. So its reaction with cement is so faster than some other admixtures that we use in this experiment. Then the void volume, how permeable is the material? How permeable is the material? From the experiment, it shows the permeability of the material, and even at 900 degrees Celsius, the percentage of increase from that of control is still minute, because the difference in the value are not so significant. And if you see from the ABC, it shows the level of significance of those materials. Now, we carry out the fiber interaction of the composite types. We want to see what's happening between the fiber and the matrix. Because when you introduce a fiber into a composite, you want to see whether there is a good bonding interaction between the material. For example, this microstructure shows the microstructure of fiber-matrix interaction between rhizosa and eggshell. And now you can see some pores. The arrangement of pores around the fiber in this place is very minimal. I'll show you that further. Look at the one for calcium carbide pores. The arrangement of pores around the fiber are so many compared to what we have with the one with incorporated with rhizosa and eggshell born at 900 degrees Celsius. And this is for the one that contains the three, because we use the three: the rhizosa, the calcium carbide with the eggshell and the cement as a bonding. But we find that particular hand has a lot of pores, because the more you increase the material mixture, because rhizosa has its own chemical composition, calcium carbonate has its own chemical composition, eggshell has its own. So the more you increase, because most of those materials, it's not that they are perfectly compatible, but we are just trying to see how best we can improve the property of material. And we see that from this microstructural characterization, see that the sample that contains rhizosa ash and chicken eggshell have the best performing characteristics, because the void area around the root of the fiber and the matrix is very minimal, is very minute compared to other materials. Now, in the conclusion of this presentation, now it can be concluded so far that replacement of cement with admixtures of rhizosa, calcium carbide waste, and chicken eggshell result into growing on less denser composite types. We check from the sort of the density, the bulk density of the composite type. We discover that all the admixtures produce material with lesser density than their control. Then we see from the result of the experiment that carbonation improves the both physico-mechanical properties of fibre-reinforced composite types, which I've explained in the earlier slide. Then hydrolysed chicken eggshell, which I explained, that conversion of our eggshell from calcium carbonate to calcium oxide to calcium hydroxide helps in better performance of Modulus of Elasticity, Modulus of Rupture of composite type. Then, from the whole summary of the experiment, which of the raw material performed from the experiment, checking all the physical and mechanical properties of the material, it can be concluded that admixture of rhizosa and eggshell show a better fiber-matrix interaction than all other populations. Thank you for this.
Thank you so much. So I would like to invite for questions. If anyone has any questions, just please raise your hand or otherwise type it in the chat box. Okay. So I think nobody is is having any questions, but I would like to ask you one thing. Perhaps coming from Nigeria, I know that, or this is at least the story that I know, that oil palm is originally native to Nigeria. It has been exported to Malaysia,
Malaysia.
Indonesia.
Yes.
But I was just wondering of the status of the oil palm and the utilization. I've seen you and Professor Abel doing your work on like rattan and coconut, but is there, I mean, like a population of oil palm and oil palm industry in Nigeria?
Oh, thank you, Dr. Mohammed. That's a very sound question. From history I read, truly, Malaysia got their seedlings from Nigeria, which has made Malaysia one of the best oil producing country in the whole world. But you know, one of the problems we have in Nigeria is government policy, and maybe because of the advent of crude oil that the nation has, there's a diversion of purpose. In those days, in the early 70s, all the railways, the airports, all the monuments built in Nigeria were built from agricultural waste. No, from agricultural produce. In fact, from what I read in those days, that oil business in the southern part of Nigeria is the most richest business in West African part of the world. But now, because there's oil everywhere and oil is the main thing in the global market, the attention of government has been diverted. But I think with the trend of collapsing oil price globally now, the government of the day is trying to preach a new sermon to the citizens, whereby everybody has to go back to the farm. And in fact, there are some state governments that has to go back to Malaysia now to go and learn. Can you see the wave? They came to Nigeria to come and pick our seedling. They are thriving there now, but we have to go back to them to go and learn because our government they don't have a data plan of what they have for the nation. There's no rigid agenda. There's no plan. There's no plan for the future. It's because of the advent of the program.
Yes. Thank you so much, Dr. Anthony, for your insightful participation.